Educational videos by MMS programs civil.com. Please visit website mmsprogramcivil.com for videos. Design of one-way continuous slab. Continuous slab. As according to clause 22.4.1 IS 456-2000, arrangement of imposed load. A consideration may be limited to combination of first, design dead load on all span with full design imposed load on two adjacent span. Okay, this will give you the maximum negative moment. Over here, you have to take design dead load plus live load into 1.5 times, and over here you have to take full dead load only, right? Design dead load on all span with full design imposed load on alternate span. This will give you maximum positive moment. Apply maximum load on alternate spans, that is 1.5 into dead load plus live load, and on other span you have to apply only dead load, right? When the design imposed load does not exceed three-fourths of the design dead load, the load arrangement may be design dead load and design imposed load on arrangement may be applied. Okay, when the design imposed load does not exceed three-fourths of the design dead load, the load arrangement may be design dead load and design imposed load on all the spans. Okay. Apply design load on all spans, that is 1.5 into dead load plus live load. So this is how you have to try for different combinations and form an envelope from which you have to take the maximum positive and negative bending moment and shear force, for which we have to design one-way continuous slab or continuous beam design, right? Code has suggested an simplified approximate method of analysis, structural analysis of one-way continuous slab with UDL using code coefficients. This can be also used for continuous beam, right? One-way slab of uniform cross-section are designed as beam of 1 meter width. Okay, you have to take 1 meter width as your design strip, for which you have to design one-way continuous slab. Code has given coefficient for calculation of moments and shear for continuous beam or slab with uniform loading. The continuous beam should have at least three span. There should be at least three span. Spans are considered to be equal if the difference in the span is not more than 15% of the largest span. The span should not differ more than 15% of the largest span. The continuous beam should have at least three span, right? Okay. These coefficients for the ultimate moment and shear are given in table 12 and 13 of IS 456-2000. And very important note that once you, whatever moments you find from using these coefficients, there cannot be redistribution of these moments. Okay, so no redistribution of this moment is permitted further, right? Okay. So this is the table for finding the bending moment coefficients, type of loads. Uh, this is dead load plus live load fixed, that are permanent loads. This is live load not fixed. This can be also called as moving loads. Okay. Okay. So this is our continuous one-way continuous slab. One-way continuous slab. This is the end support. This is support next to end support. This is intermediate support. Okay, or this is end span. This is interior span. Okay, in this case you can see this is end support. This is support next to end support. This is end support. This is support next to end support. If you have a support in between, then that will be your interior support. Okay, so we have been given coefficients. For obtaining the bending moments, this coefficient shall be multiplied with the total load, capital W in kilonewton, with effective span. But we are having a UDL whose unit is kilonewton per meter, that's small w. So small w into L will give you capital W, right? So in our case, we will take small w into L, that's L square, right? Small WL into L, that is WL square. Okay. Now this are the span moments, that is sagging moments. Sagging moments, we take it as positive because in that case tension is at bottom. Okay, so near the middle of the end span, So this is your end span. So near the middle of the end span, near the middle of the interior span, this is your interior span. So this is near the middle of interior span. Similarly, support moments, they are hogging moments. They are negative because tension is at top and they will give us negative steel. At support next to end support, this is end support. This is support next to end support. Okay. And at another interior support. So these are other interior supports, right? Now let us see how do we apply these coefficients. So let us start with this near the middle of the end span. Near the middle of the end span. Okay. So uh, this is dead load divided by 12 plus live load divided by 10 into L square. Okay. So dead load divided by 12 plus live load divided by 10 into L square. Similarly, at the middle of the interior span, dead load divided by 16 plus live load divided by 12 into L square. Okay, so this is load. W, that is, this is load, right? Okay, so these are sagging moments. Similarly, you can have the support moments. Okay, so for this support, you will have one moment over here for this span and one moment over here for the span, right? So this is your support next to end support. So this is negative because this is hogging moment. Okay, so you will have dead load plus dead load divided by 10 plus live load divided by 9. Okay, so dead load by 10 plus live load by 9 into L square, carrying a negative sign. Okay, because this is a hogging moment. So this will be acting over here and this will be acting over here, right? So the magnitude will depend upon the span. Okay, uh, so this moment, say this is 4 meters, this is 5 meters, then over here this is 4, there will be 4 square, over here there will be 5 square. Okay, so the magnitude of the moment will depend upon the span, right? Fine. Similarly, at another interior supports, this is dead load divided by 12 plus dead load divided by live load divided by 9. Okay, so that will be acting over here and acting over here, right? So this is how we get the bending moments at supports and the mid span, right? Now, code also says when a member is built into masonry wall which develops only partial restraint, then the member shall be designed to resist a negative moment at the face of the support, which is equal to capital WL divided by 24. So when your end support is a wall, right? Then code says you have to take a moment which is equal to WL square by 24. This is small w, right? But in practical field, many times we see that continuous slab is supported on beams. Okay, in that case, this has to be taken as shear case of simply supported, so that the moment over here is to be taken as zero. So that the twisting moment in this supporting beam will be zero, right? So in this case, no extra topsail is provided over here, and uh, and this is based on the assumption that whatever the supporting beams we provide are very rigid in nature, right? So note the support should be fairly rigid and should not deflect by themselves. So this is a very important assumption. So when a continuous slab is supported by beams, okay, then they have to be very rigid. Okay, then only this coefficient can be applied. Now shear coefficients, right? Again, dead load plus live load fixed, and this is live load not fixed. So let us first understand. This is end support. This is end support. Now this is support next to end support. This is end support. This is support next to end support. This is interior support, right? So these are the coefficients for end supports. These are the coefficient for the outer side of the end support next to end support. Outer side means the side towards end support. Inner side means the side towards interior support. Okay, so here outer side is towards end support. Inner side is towards interior support. Now how to obtain the shear force? For obtaining the shear force, this coefficient shall be multiplied with the total load, that is capital W. Now we are having UDL, that is small w kilonewton per meter. So to convert it into total load, we have to multiply it with span. So we'll have to take small w into L, right? So the shear force at this will be zero point 0.4 into dead load into span plus 0.45 into live load into span. All right. So that is what is shown over here. Okay. Uh, at this outer side, it will be zero point 0.6 into dead load into span plus zero point 0.6 into live load into span, right? So this will be this reaction. Now this reaction over here will be 0.55 into dead load into span plus zero point 0.6 into live load into span, right. So this outer reaction will be applicable over here also, and this inner side reaction will also be applicable over here also, right. For interior support, you will have one reaction over here for this span, one reaction over here for this span. Okay, that will be zero point 0.5 into dead load into span plus zero point 0.6 into live load into span, right. So this is how we find the shear force. Okay, choosing effective span by effective depth. Okay, that is ratio. Slab are thin members, and so deflection will govern the depth. Okay, IS 456 2000 clause 23.2.1. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained as below. A basic value of span to effective depth L by D basic ratio for the span up to 10 meters. This is all which we know very well. For cantilever it is 7, for simply supported it is 20, for continuous it is 26. So the total actual L by D allowable is equal to L by D basic into KT into KC. Okay, where KT and KC are the modification factors corresponding to the percentage of tensile steel PT and the percentage of compression steel PC, right? Okay. Now, the slab thickness is very small in comparison to that of beam, and L by D ratio generally governs the proportion. In practice, Fe415 and Fe500 are the most commonly used steel, and for such steel, PT value is assumed about 0.35% to 0.5%. For this value of PT, KT generally has value of 1.25. So for selection of the assumption of the depth, effective depth of the one-way continuous slab, you can take KT as 1.25 at the initial stage, and the LD ratio of the simply supported slab works out to be, this is LD basic, that is 20. Okay, this is 20 into KT into KT. KC is taken as 1 because there is no compression steel in slab. So when there is no compression in steel in slab, then KC value of KC will be 1. Okay, so that is why you can start with L by effective depth ratio is equal to 25 in case of simply supported slab. For continuous, you can take 26 into 1.25, that is 32, right? So in order to determine the overall depth of the slab, clear cover plus half the diameter of the bar is added to the effective depth D. Whatever overall depth you get is rounded off to the nearest multiple of 5 mm or 10 mm. What I mean is, say suppose you got your effective depth D as 200 over here, then add half the diameter of the main steel plus the clear cover. That will give you the overall depth, right? And that is to be you have to select this to the nearest multiple of 5 mm or 10 mm. Okay, that is what is done in practical field. So let us move further. Okay, so let us start with the problem. Design a continuous one-way slab with 3 spans using chord coefficients. The effective length of the first span exterior from the left is 4.5 meters. Okay, so let us see over here. This is first span, that is 4.5 meters, right? This is your first span, 4.5 meters. Now, then the effective length of the second interior span is 5 meters. So this is 5 meters. Okay, fine. And And the third span exterior from the right is 4.5 meters, right? So again, this is 4.5 meters. Okay. The slab has to carry a live load of 4 kilonewton per meter square, and the dead uh, weight, excluding the self weight of the slab, is 1.5 kilonewton per meter square. Take concrete mix as M20 and use HYSD FE415 for design. Okay. So given to us solution that F5 is 415, FCK is 20 Newton per mm square. Assume the effective depth D of the slab using the ratio span by effective depth for continuous beam is 26. So we will take in consideration the longest span, say 5 meters. So L is equal to 5 meters. I am starting with the assumption effective depth is equal to 200 mm. And I am assuming that I am going to use 10 dia bar as my main steel. So half of that is 5 and 20 is the clear cover. So my overall depth is 200 plus 5 plus 20, that is 2 to 5 right? So I can find the self weight of the slab, which is 5.625 kilonewton per meter square. Live load given is 4 kilonewton per meter square. Dead load given is 1.5 kilonewton per meter square due to floor finish and partition wall. That is furniture partition wall. Okay. Total design load will be 1.5 into live load into dead load into self weight. That is equal to 17 kilonewton per meter square. Okay. Okay. So according to the clause 22.5.1, unless more exact estimates are made for beam slab of uniform cross section which supports substantially uniformly distributed load over three or more spans which do not differ more than 15% of the longest, the bending moment and shear force used in design may be obtained using the following coefficients. Right? This is what which this is what we have already seen. Right? So we can see in our case, okay, uh, the span do not vary more than 15% of the longest span. So we can use these coefficients, okay, as we, there are already, and also we have at least three span. So we can use the coefficients given in the code, right? So we will start with the bending moment, okay. So this are the coefficients which we are going to use. Okay. So first we will find the end span moment, that is sagging moment at near the middle of the end span. So this is your M1, right? M1 is found as, okay, a dead load divided by 12 plus live load divided by 10 into L square. Okay. So this is what I have found over here. Dead load by 12 plus live load by 10 into L square. This is 4.5. So this is 30.71. Similarly, M2 is the hogging moment at the support. Okay. So support moment at support next to end support. Dead load by 10 plus live load by 9. Okay. This is going to be negative because there's a hogging moment. Okay. So dead load by 10 plus live load by 9. Okay, over here we have two spans. This is common support. Over here the span is 4.5, over the span is 5. So for getting the larger moment, we will take the larger span, right? So that is why we'll design this support for the larger moment. That is why, right? So we are taking span as 5, okay? So L square is 5 into 5. This is 44.16 kilonewton meter, right? Similarly, M3 is the moment at the middle of the interior span. So dead load by 16 plus live load by 12. Okay. So this is how we get this. Okay. That is 29.68. Now, the code says, okay, okay, say if this slab was, if this end span was a beam, then definitely we will consider this as a simply supported and will take moment over here as 0. But we know that our slab is supported on a masonry wall. So the code says in that case, you have to take at least a moment of W, capital WL divided by 24. So dead load by uh, L square divided by 24. So that is equal to 14.35. Okay. This is small w. This is because the unit is kilonewton per meter. So that is why W into L, that is WL square divided by 24. So this is how we got the moment over here, here, and here. So now we will do the design, right? Okay, so this is the table. M1 is 31, M2 is 44.16, M3 is 29.68, and moment at the end support is 14.35, right? So you can find the steel AST, right? Tensile steel by using this formula. This formula is applicable to all the rectangular singly underinforced sections. Okay, so we know that our slab is a rectangular section, and we are assuming that it is going to be underinforced, and we'll check whether it is underinforced or not. So we are using this formula. Using this formula, put the value of moment over here. You get the value of required steel. Okay, this is the required AST. So 460, 660, 431, 204. And now this is less than AST minimum, which should be 0.12% into cross section, overall cross section of the slab. So that is 270 mm square. So instead of 204, we will have to take 270, right? Fine. Now we have to find AST provided. Okay, this is the formula for finding the percentage of tensile steel. This is the formula for finding the spacing, center to center spacing of the bars. Okay, so this is width of the strip, area of the bar to be used divided by AST. Okay, fine. So over here, when for M1, this is still required. So we are going to provide 10 mm dia bar about spacing 150 mm, right? So let me show you over here the section, right? So this is your M1. So for this, we have to provide the steel at the midspan, right? So this is the steel which we have provided 10 mm about 150 mm center to center over here. So the spacing between this and this is 150, this and this is 150, this and this is 150, right? So one bar I am taking continuous, and another bar I am taking I am curtailing over here and over here, right? So what should be this distance, right? So over here, this steel is this steel, okay, and the distance of this curtailment you can be taken from the this figure which is given in SP 34, okay. So this bar can be curtailed at a distance 0.15 L, and this bar can be curtailed at a distance 0.25 L. Okay, so that is what 0.15 L and 0.25 L. Okay, so that is how we place this positive steel over here, right? Now coming to the next, that is M2, that is your M2 is hogging moment, steel at the top required. This is steel required for M2, right? Okay, so M2 is we are providing spacing 10 mm dia about 115 mm. So this is your top steel, right? You can see this is a top steel. This steel is also provided over here, right? So this is 10 mm about 115 mm. So this is 10 mm about 115 mm, right? Okay, fine. Now coming to M3, right? M3, we are providing again same spacing over here as to keep the continuity and symmetry. Actual spacing may be a little bit lesser, required maybe little bit lesser, but for the case of sake of uh, symmetry, we will keep the spacing same. Okay, so this spacing we are keeping as 10 mm about 150 mm center to center. Okay, fine. So this is the moment near the midspan. So this is the main steel over here, and we are providing 10 mm about 150 mm center to center at the bottom, right? Fine. So now we have this steel is again same repeated over here. So now we have designed our bottom steel, we have designed our top steel. Now we have to design our steel at the support, right? So at support the moment is less. At support the moment is 14.35, and the steel required we are providing is 10 mm about 300 mm center to center. So we will be providing 10 about 300 center to center over here and over here. Okay, that is this steel and this steel, right? So this is how we do the detailing. Okay, and we'll have distribution steel in this direction. That is, we are going to provide 8 about 180 center to center bottom distribution steel. This round dots which are shown over here are the distribution steel, right? And let us see an 3D view of this, okay, of a general diagram. Okay, so this is how you can also give bent up, right? You can take one bar you can run straight, and one bar you can take a bent up, and again from here bent up, again straight, again bent up, like this, right? Let me show you over here, right? One bar is straight and another bar is bent up like this, bent up like this, right? And then you can provide one bent up like this and one straight bar like this, right? Fine. So the distance from where this bent up has to be taken is 0.15 L over here, and from here it should be 0.25 L, which we just saw, right? Which is given in over here, 0.25 L and 0.15 L. Okay, now how to find the length of this extra top bar? Okay, so code says take this as zero point 0.3 L plus zero point 0.3 L plus the width of the beam, right? So that is going to be this distance. Okay, that is going to be this distance. Okay, this extra bar. If you can see this extra bar, right? Fine. So this is how you can also provide bent up like this. Okay, this is another type of orientation of steel. Both are correct. You can use any of this. Fine. Fine. So this is how we do the design of one-way continuous slab, and this is how we place the reinforcement. Okay, that is what I explained, that how to show the reinforcement detailing. Now coming to the next step, now we have to go find the shear, right? Now this is dead load plus live load at the end support, right? Fine. This is end support. This is for support next to end support. This is support next to end support. This is out. This is outer side. Outer side. This is inner side. This is inner side. Again, this is support next to end support. This is end support, right? So this is outer side. This is inner side. Okay. So we have to find end support reaction, outer side reaction, inner side reaction. Okay. So same thing will be repeated over here. So let us start with that. Okay, as I explained, if the slab was supported on a beam at the end support, then this were the coefficient which we had to take. But our slab is supported on wall. Okay, so in that case, the code says that the end where a member is built into a masonry wall which develops only partial strain, the member should be designed to resist negative moment at the face of the support of equal to capital W L by 24, which we already did, where L is the total design load and L is the effective span, or such other restraining moment as may be shown to be applicable. For such conditions, shear coefficients given in table 13, this table 13, at the end support may be increased by 0.05, right? That means you have to increase this 0.42 to 0.45 and this 0.45 to zero point 0.5. You have to add 0.05, 0.05 over here, okay? Because in our case, the slab is supported on a wall, right? So our end reaction will be, okay, zero point 0.4 plus 0.05 into dead load into span. So I'm adding 0.05 over here. Now 0.45 plus 0.05 into live load into span. Okay, this is your live load. Shear force due to live load, shear force to dead load. Add this, you get the total shear force, that is 35.77. Similarly, over here, zero point 0.6 into dead load into span plus zero point 0.6 into live load into span. Okay, so zero point 0.6 into dead load into span, zero point 0.6 into live load into span, total is 45.9. Okay, now for inner side, right? For inner side, it is zero point 0.5 into dead load into span plus zero point 0.6 into live load into span. Okay, 0.55, sorry, it's 0.55, sorry. Okay, it's zero point 0.5. Okay, 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 okay. Uh, this is zero point 0.5. Okay. Okay, zero point 0.5 into dead load into span plus zero point 0.6 into live load into span. Okay, this is little, instead of zero point 0.5 I've taken zero point 0.5. This is going to be a little bit more, so it doesn't matter, it's going to be more safe. Okay, this is going to 48.25 kilonewton, right? So this is how you find the shear force. Okay, so this shear force I have written over here. Okay, now you can find the nominal shear stress, that is tau v, that is v divided by bd, right? So B is 1 meter and D effect depth is 200 mm. So we find tau V as shown in the table, right? Now, in case of slab, tau V nominal shear stress should be less than tau C, okay? Because in slab we do not provide shear reinforcement, so all the shear has to be taken by the concrete and the tensile steel, right? So tau C in case of slab is equal to K into tau C. K is the overall depth factor of slab. Our overall depth is 225, so K will be 1.15, right? So tau c is K into tau. This tau c has to be found from table 19 plus 40.2.1.1 IS 456 2000 for the corresponding percentage of steel PT, right? So I have checked. This tau c is found to be greater than this tau v, so the section is safe in shear, right? Another thing the code says that this tau v should not be greater than the solid, for solid slab the nominal shear stress shall not be and shall not exceed half the appropriate value of the following table in 20. This is tau c max, right? These values are applicable to beams, but when it comes to solid slab, then you have to reduce this value by 50%, right? So tau v should be less than zero point 0.5 tau c max. So this is also very important, right? Usually, in most of the cases of slab design, one-way shear is found to be within permissible limit. If not found, then you will have to either increase the percentage of tensile reinforcement or increase the depth of the slab, as we do not provide shear reinforcement in case of solid slabs. So this is very important, right? Okay. So next step is we have to do the check for the deflection. Now we will do the check for deflection at the midspan, definitely over here and over here. That is for moment M1 and moment M3, right? So we can see from this table, let me go above. So this is moment M1. This is our required steel and this is our provided steel, okay? And this is the percentage of steel we have provided, PTO, okay? So this three values we are going to use for doing the check for deflection, right? For M3 also, the same the required is 431, provided is same, okay, and PT is also same because we are providing same steel, so PT will remain also the same, right? So this is the value. Please remember this is 460 and this is 523 and this is 0.261. Okay, so these values we are going to use. Okay, so first we will start with M1. Okay, so moment M1 is 31 kilonewton meter. We know this formula, L by D max is equal to L by D basic into KT into KC. For continuous beam, L by D basic is 26. We know our PT is 0.261. So we have to find the stress in steel. This is the formula given in the code for finding the stress in steel. This is the area of cross section steel required. This is provided. This is we have what we saw in the table. This is required and this is provided, right? So this comes out to be 211.57. So this will fall between these two graphs, right? So you can draw a line for PT 0.261, okay, and you get KT is 1.7, right? So KT is equal to 1.7. Kc will be equal to 1 because there is no compression steel. So when the percentage of compression steel is 0, Kc will be 1, right? So you can find this now. This is equal to 44.2, right? 26 into 1.7 into 1. Now L by D actual for the first span, that is this span, this is 4.5 meters, right? So 4.5 divided by effective depth is 200. Okay, so 4.5 meters divided by 200 is equal to 22.5, which is less than 44.2. So it satisfies the deflection criteria, right? So let us check for M3, that is 29.68. This is the formula, and this is the basic L by D basic. PT is again same 0.261 as we saw in the table. Find your FA will also be again same, so KT will also be again same. Okay. uh, Actually, there will be slight difference in FA. Okay. Because let me show you the table. This required steel is 460, and over here the required is 431, provided it's same, right? So this will be slightly larger, okay, but still that will not make much difference, and we can take KT same as in the case of first, right? As we found the KT for this and at the for this moment, okay, we can use same KT for this moment also, right? Because the difference is not going to be much. Okay, so KT is equal to 1.7. Okay, so again this will be 44.2. Now the mid span, that is interior span, this span is 5000, 5 meters. Okay, D is 200, so this is 25. This is again less than 44.2, so this is again satisfying the deflection criteria, right? So for design of continuous beam, please watch video design of continuous beam on website mmsprogramsil.com. I hope you must have found this video, that is design of one-way continuous slab, useful. Thank you.